Hello everyone, today I'm going to talk to you about the online SNR statistics estimation for AWGN decoding over AWGN channel using Laplace Propagation. Here is outline of today's presentation. First, I give you a concise introduction about the problem statement, previous work, and our contributions. Second, I will present the problem modeling of the proposed adaptive AWGN decoding framework on fact graph, and point out the difficulty that exact inference based on the proposed fact graph is intractable. Then I will introduce the approximate inference, a workaround to solve this difficulty, where I will cover both stochastic and deterministic approximation method. After that, in the fourth section, I will present the proposed adaptive AWGN decoding for channel noise estimation using Laplace propagation, which is a deterministic approximation method. Finally, I will show you our experimental result and draw the conclusions. For the introduction, let's take a quick review of the channel coding problem. Suppose we have channel input X coming from the channel encoder and some channel output Y, and here we consider adaptive white Gaussian noise channel, short for AWGN, which means that the channel output is equal to the channel input plus a Gaussian noise with zero mean and variance V. In practice, the decoding performance in channel coding problems relies on the knowledge of the channel state information. To obtain the perfect knowledge of channel noise, we can use a pilot signal or feedback channel. However, a fast varying channel implies potentially a large conditional overhead. Another solution for this problem is to perform channel state information estimation at the decoder side. In this study, we focus on the noise variance estimation of the AWGN channel using LDPC code. Since the ability of performing channel state information at the decoder side is very important, there are many previous work studied on this problem. However, most previous works assume that channel noise is a constant. In practice, the channel noise may vary over time. Therefore, in our study, we consider a time-varying noise model. Moreover, in our study, we use Bayesian paradigm for channel noise estimation. In contrast, most of the previous works are using non-Bayesian paradigm, which means that the learned knowledge from the current time cannot be used in the future learning process. In addition, we use deterministic approximation method named Laplace propagation to solve the proposed model. As a deterministic approximation method, the Laplace propagation algorithm only introduces a short decoding overhead comparing with sampling method. Finally, the proposed algorithm can perform estimation and decoding simultaneously, which means the updated estimate can be used to improve the decoding performance, and vice versa. In most of the previous works, the estimation process is performed before the start of decoding. In the next section, I will present adaptive AWGN decoding on factor graph. Now, I will show you how to build a factor graph for the AWGN decoding. We first write down the channel output Y using the white circle, since Y is observation. Here we suppose that the code length is 7. Then the channel noise can be captured by the factor function of the factor node Fi, or with argument xi, yi, and variance v, and this factor node connects the observation node yi and the variable node xi. Then our goal is to find a vector x hat, which satisfies the parity check constraint. And this constraint is captured by the fact node hj, j from 1 to 3 here. Then, given this fact graph, we can use the amplification algorithm to efficiently compute the marginal probability of each variable. The belief propagation algorithm can be summarized as follows. First, for the variable node update. Suppose we want to update the message from the xi to the fact node hg, then we just simply multiply all the incoming messages except the message from the fact node we want to update. For the fact node update, we multiply the factor function and all the incoming messages except the variable node we want to update. Then sum over all of the variables except the variable we want to update. Then we iteratively update variable nodes and factor nodes until all the messages converge. Finally, we can calculate the belief of each variable by multiplying all the incoming messages. Here, the belief is a marginal distribution of the variable. Finally, we can make our final decision based on the belief, where x hat is equal to 1 if the belief of xi equal to 1 is larger than the belief of xi equal to 0. Otherwise, we set x hat equal to 0. Please be noted that both in the variable node update and the belief update, we use the message sent from the fact node fi to the variable node xi. And in the LDPC decoding, this message is equal to the output of this factor function, since y is observation. For a AWGN channel model, this factor function can be expressed as follows. And here, we're using the relationship between the precision and the variance. We use lambda to denote precision, and v is the variance. So in this factor function, it includes the argument xi, yi, and precision lambda. And we can see that the parameter lambda is given as a constant in the traditional model. And if we have the perfect knowledge for the correlation parameter lambda, then the LDPC code can achieve an ultimate decoding performance. However, in reality, such information may not always be available at decoder. Therefore, the decoding performance of LDPC code will be degraded. To solve these problems, we propose a time-varying noise model, which means that the noise variance or the noise precision could change within the LDPC code block. To capture the time-varying noise, we introduce additional variable nodes, pj, and corresponding fact node, gj. And the factor node gj is used to provide the prior information to the variable node, pj. Then the message from the factor node fi to xi will be reformatted as an integral, since we have the message sent from the variable node pj to the factor node fi. Moreover, in the factor function fi, there is a one more argument lambda precision, which denoted by the variable node in this figure. And this precision can change over time. So in our model, each variable node pj can connect a certain number of factor nodes fi, and In this figure, each variable node Pj connects a full number of the factor nodes. If the number of the neighboring factor node of variable node Pj is small, then the variable node can be used to capture a fast varying noise precision. Otherwise, it can be used to capture slow varying noise precision. If there's only one variable node Pj, then the proposed model can be used to estimate a constant correlation. Given the fact graph with time noise statistic estimation, we can perform inference on the fact graph. For example, let's consider a AWGN channel with a noise precision lambda j. Since we consider a binary code, then the variable x can take a +1 and -1. Thus, the message sent from the fact node Fi to the variable node Pj is a mixture of two gamma distributions. Here, I need to mention that this factor function, if we taken the precision as a variable, then the factor function can be reformed as a gamma distribution. So the message sent from fact node Fi to the variable node Pj, according to this equation, is equal to the mixture of two gamma distribution, as shown in this figure. Then, if we write down the belief of the lambda j and substitute the message from the Fi to the Pj with mixture of two gamma, then we can see that this belief of variable lambda j is mixture of two full number of gamma distributions. This is a 16 number of gammas. Since there are 4 neighboring factor nodes on the right-hand side, and in practice, the number of neighboring factor nodes of a given variable node Pj can vary from 100 to 10,000, which means to perform exact inference on the lambda j, one need to evaluate 2 to 100 or even 2 to 10,000 number of the gammas. And in this case, the traditional propagation algorithm is no longer tractable. And therefore, we need to resort to some approximation inference method. For the approximate inference, there are mainly twofold: the stochastic approximation and the deterministic approximation. For the stochastic approximation, it's usually called the sampling method. And the advantage of sampling method is that it can be used to approximate any distribution. However, sampling method in general very slow and require a large amount of computational power. In contrast, deterministic approximation is very fast, but it works only on simple, smooth distribution. Moreover, the accuracy of deterministic approximation is usually unpredictable. But for sampling method, as long as we have enough computational power, we can obtain a very high accurate approximate. And in this study, we mainly focus on the deterministic approximation due to the low complexity property. And let's first start with overview of deterministic approximation. There are mainly 3 different methods. The Laplace approximation, we will match the mode between the exact distribution and the approximate distribution. In the variational Bayesian, we will match the lower bound. In the expectation propagation, we will match the moment. And in our study, we're going to use the Laplacian approximation. Now, I will explain how to perform the mode matching in the Laplace propagation. Suppose we have an exact distribution P of x, which is the unimodule non-Gaussian distribution. Then the Laplace approximation will try to use a Gaussian distribution Q of x with mean, mu, and variance v to approximate the exact distribution P of x. And here we introduce a projection operation, which makes sure that the true distribution P of x and approximate distribution Q of x have the same mode. Then the approximate distribution will have then we will calculate the mean and the variance of the approximate distribution according to these two equations. Now I will give the big picture of the Laplace propagation. We will take a look at how we use the Laplace propagation or mode matching to approximate multimodal likelihood function. Let's first consider a naive case in which the projection operator is directly implemented on the likelihood function. So it means that for this likelihood function, according to the mode matching, I will have a Gaussian distribution to approximate this likelihood. And we just mentioned that the approximate distribution and the true distribution will have the same mode. And for this likelihood, it has two modes. If we choose the right mode, then given the prior distribution in this middle figure, we can obtain a good approximation posterior. And in contrast, if we choose the left mode, and with the prior distribution, we will get approximate posterior distribution, maybe around here. It's not a good approximate. So now we will consider another informed case. If we know the prior is on the right, we only need approximate distribution Q of x which can fit the right module of this likelihood function. Then we can get a perfect approximate of this posterior. In other words, we only need to select a spot of the likelihood function where we really need to approximate. And here is a detailed procedure to perform the Laplace propagation. The key idea is to perform project operator on the product of likelihood and prior, instead of directly on the likelihood function. Now, let's return to noise precision estimation problem. In this study, we consider a AWGN channel, and the likelihood function is shown in this equation, and we'll just show that in the previous slides, respect to the lambda j as variable, then this equation can be rewritten as a gamma distribution. To make the inference have the closed-form solution, we choose the gamma distribution as the prior, since it's a conjugate prior of this likelihood function with precision as unknown variables. Then we approximate this true method sent from the fact node Fi to the variable node Pj, which is a mixture of two gamma distributions. We approximate this method by this method is called M tilde, which is a single Gaussian distribution using the mode matching algorithm. Then we get this approximate posterior and get the estimate precision of lambda j. And here, this is the procedure of Laplace propagation algorithm. And first, we initialize each factor fi tilde and the posterior distribution, which has the n number of the factors. And then for each factor fi, we will remove it from the posterior distribution. So we get the q naught I is equal to the q posterior distribution divided fi tilde. Then we perform the Laplacian approximation to update the q posterior distribution qc, using between the qc and the true factor fi times the q naught I. Then we get the updates the parameters mean and variance of the posterior distribution. After get the updated posterior distribution, we divided the q naught I. So actually, we also updated the term fi. Then we continue to consider the second term, then the third term, then we continue until all the parameters converged. So this is the basic procedure of the Laplace propagation. And in the following, I will show the details of the Laplacian propagation in our problems. And here in our problem, the likelihood this is the likelihood function. How to do the Laplacian approximation? So here, suppose we want to consider the factor fi, one of these factors. Then we get the q naught fi is calculated from the posterior distribution divided fi. And then this term is the true message sent from the term fi. Then this q naught fi is assumed the Gaussian distribution. Then this true term is a factor function times this method and sum over the variables xi. So actually we just mentioned that it's a mixture of two gamma distributions respect to the lambda j as a unknown variable. So here we did some calculation, and then finally we got these two terms. And in the following, we will assume that the message sent from variable node xi to fact node fi with xi equal to -1, divided the message with xi equal to 1, and is IRX. And then, given the posterior distribution, we want to use a Gaussian distribution to approximate. So we need to calculate its mean and variance. So to make sure that approximate distribution and the true approximate distribution have the same mode in the Laplace approximation, first we need to calculate the mean, And to make sure that they have, to make sure that the true posterior distribution and the approximate posterior distribution have the same mode. Here, we're just to make sure that the first derivative of the posterior distribution respect to the lambda j is equal to 0. So, following some calculations, we get here, and we can guess the point lambda 0, and it is also the mean of the approximate posterior distribution. Then, based on this mean, we can calculate the variance of the posterior distribution, and we need to calculate the second derivative of log posterior distribution respect to the lambda j, as the point lambda j is equal to lambda 0. So here we have some relationship with the first derivative of the posterior respect to the parameter lambda. So here we can easily calculate the variance. So after these two calculations, we can get the mean and the variance of the approximate posterior distribution. So then this is finished for this term. Then we continue the second term, and then we calculate the mean and the variance. Then we will iteratively to update the posterior, and also we update the each terms. Then we can finally calculate the estimate precision when all the message converged. Then in the following, I will show the result of our adaptive LDPC decoding using Laplace propagation. And I think the first, I will show the estimation performance of the proposed LP estimator for time varying SNR, and we can see that here this solid line is a true precision, and this dashed dot line, this dashed line is initial precision, and this dashed dot line is the estimate precision. So we can see that the Laplace propagation estimator provides a very accurate estimate of the time varying noise. And now I will show you the decoding performance in the presence of SNR mismatch for time varying noise model in terms of the bit error rate vs the SNR. And here, the decoding performance of the LDPC decoder with perfect knowledge of SNR is given as a reference. Shown at this curve. And then the initial SNR is considered in two cases. The first case is equal to the mean of the time varying SNR, and shown on the left figure. And the second case is the initial SNR is 2 dB away from the mean of the true SNR, shown on the right figure. So when the mean of true SNR is used as the initial value, we can see that the proposed LP-based LDPC decoder slightly outperformed the ordinary BP decoder. So we can see these two curves are very close. But we can see that there's a big performance gap when the proposed LP-based decoder and the traditional BP decoder, when the initial SNR has the 2 dB mismatch of the true mean. So this is the traditional BP-based LDPC decoder, and this is our proposed LP-based decoder. So there is a big performance gap. So we can see that given the same initial SNR especially has some mismatch, then our proposed adaptive LDPC decoder using Laplace propagation can improve the decoding performance significantly. And here is a conclusion. And in our method, we consider time varying noise model and using Bayesian paradigm for channel noise estimation. And we use the deterministic approximation method to solve this problem, which has a very low computational complexity. And we also can perform the estimation and LDPC decoding simultaneously. So I think that's it. And any questions? Thanks.